Thank you. Well, good morning, everybody. Welcome to a new seminar held by the Geosciences Barcelona and the Faculty of Earth Sciences. And today I'm going to introduce you Petr Vitous. I did it well.
Yes, nice.
He's finishing a 3-month visit in the institute. He was invited by the former director, John Martí, and he's also collaborating with Petr Vitous and Policia Ayala. His study interest of research is the magnetic fabrics in volcanology, and his thesis focuses mostly on decoding the depositional processes and flow direction of voluminous intracaldera ignimbrite bodies of paleozoic calderas. Here he's working in the Catalan Pyrenees, in the Cadimo-Xero area, and he's focusing in the Grecia rhyolites and ignimbrites, incorporated into the red beds around the Castellana. During his stay here, he learned how to perform the method of the palamagnetism with progressive thermal demagnetization and conducted 2 field trips in the studied area to take samples. So, you want to start?
Yeah, thank you for the introduction. If there, I think that's all that had to be said before, and I'll get right to it. Well, I was invited here for this seminar. I did not know for sure what I'm actually capable of presenting. So I decided to present the one research that I completed and published, which bears the name Magnetic Fabrics of Rhyolite Ignimbrites, Real Complex Emplacement Dynamics of Pyroclastic Density Currents. The example is from the Altenberg Teplice Caldera in Bohemian Massif. Does it work? Sorry. Never mind. Oh. This will work now. Yes. 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 During this presentation, I will walk you through it. Well, basic terminology that is necessary. Probably not everybody studies volcanoes, and then I will explain the geology of studied area, methodology used, results, and what comes from these results. In the beginning, let's just explain what are actually collapsed calderas. When you have a volcanic system, complex one, and the magma chamber that's feeding this system gets emptied, the surface loses let's say loses balance and collapse into itself, collapse into the magmatic chamber, which can happen during a big cataclysmic eruption, and very often it also produces big masses of pyroclastic density currents. These are just hot mixtures of gases and volcanic material that travels very fast, 100 to 200 kilometers per hour, one of the most deadliest parts of volcanism. And when they're stopped and they get solidified, these rocks that are formed are called ignimbrites. Because these are first of all, they are rare, so they do not happen very often. And secondly, when they happen, they're very dangerous and no one wants to be near them. So they are studied very often through older caldera systems, for example, like the one that I'm going to talk about today. And of course, this helps to overall understanding how volcanism works, volcanology, what can we do in volcanology. It can help with search of ore deposit, for example, when we look into practical things. And of course, we can still widen our knowledge of the whole humankind. The basic questions that were asked for this particular study were, what were the source vents for these ignimbrites that I studied? So what were the flow directions? Can we tell how they got deposited there? And well, overall, what is the story of these ignimbrites? What happened to this volcaniclastic that we're studying? Let's move to geology of the setting. But first, what is Bohemian Massif? Where it is? Bohemian Massif is one of the terrains that got formed during various chronorogeny, late Devonian to early Carboniferous, approximately 370 to 320 million years ago. And well, together, Iber Massif, Massif Central, and the others, they got the various chronorogeny was one of the orogenies forming supercontinent Pangaea all the time ago. And when this orogeny ended and relaxed itself, it collapsed a little bit, and a lot of magmatic activity took place. Many plutonic bodies were in place, and volcanism all over Europe was more eminent at the time. In Bohemian Massif itself, in the north, we can see there's a, well, no, yes, the Altenberg Teplice Caldera on the border with Germany. Altenberg Teplice Caldera, which is placed between the cities of Altenberg and Teplice, after which it is named. It's right on the border with Germany, which crosses the body right in half. The body itself, it's an old relic of late Variscan volcanic edifice, as previously said. And the whole magmatic history started probably 325, 319 and ended 314, 312 million years ago. So pretty much very ancient volcanic system. The whole system is elongated in north-northwest, south-southeast direction, and was collapsed in something called trapdoor style, which just means that it was collapsed more on one side. The collapse was tilted towards east. The dimensions are easily 18 kilometers to wide, 35 kilometers long. The whole evolution started by emplacement of fly monzogranite and Schenfeld-Altenberg complex, volcanosedimentary complex in Germany. Later, Seyda-Bergishubel dike swarm was emplaced in the north, mostly in the German part. And about that time, Teplice rhyolite, a large intracaldera volcaniclastic body, was also in place. During the caldera collapse itself, ring dike that delineates beautifully this caldera, thanks to which we can quite nicely see it in geologic map. It got in place well during the caldera collapse in the fracture system, and after the whole event, late subvolcanic plutonic bodies and stocks got in place, which are nowadays a source of some interesting ore minerals and such. In my case, we were focusing mostly on the Czech part of the Teplice Caldera, Teplice rhyolite, and that's for one simple reason. The border between Czechia and Germany is placed on nature frontier, which is Krušné hory mountain range, and the southern side, which is on Czech part, it's just more eroded. So here we got nice grid where we could sample the rhyolite effectively. On the German side, there are basically no outcrops. It's very hard to find there anything. A little bit of history of research of this body, because well, the overall thickness can reach up to 1,200 meters, which is quite a lot for an ignimbrite. And first, it was recognized as an ignimbrite in the 80s by Professor Holub, which so before that, that's why it's called Teplice rhyolite. They thought these were just lavas. But what was funny that before, for some reason, on Czech part and German part, the classification was different. Research was conducted differently, and there were just different classifications on both sides. And it was not until 2019 when it was unified, which was right when I was doing this research. So we had to change a bit of the classification right in the middle of the research. Here we will focus on the members that crop out only on the Czech side. I will try not to use so many different names. Some of them are even in German, so I don't know them either. But I made these abbreviations for you so you can not lost. Here we focus on the members. Teichweg on the western margin, Lukštain Pramenač right next to it, Vlčí kámen, Přední Cínovec, and Medvědí vrch. Vlčí kámen and Medvědí vrch, so the VLK and MEV, they were supposedly, when they was unified, they are supposed to be one member, but for better simplification of this study, we split them into two. What is important, because of the caldera floor tilt toward the east, the oldest in this geological map, the oldest part is the Teichweg, the most westernmost part. That's the oldest one, and it youngs towards the east. Just slightly about the petrology itself. In here, in the yellow box, there are mostly small ignimbrite bodies. In the red, it should be the bigger ones. From the yellow one, we only have the Teichweg here, and it was this nice white grayish ignimbrite with green phaeames. Phaeames are just pumices that, because of the heat and the flow, they got they flattened, they spread, and we could measure nicely their foliation, magmatic foliation, flow foliation, right on the outcrops. What was also good that this ignimbrite was right on top of asphalt tuffs, which we will later use for tilt correction. The rest, all the rest, were basically macroscopically they look the same. They're reddish, crystal rich, and that's why they thought that these were lavas, because no pumices, no phaeames were visible. Only under the microscope we can see recrystallized phaeames, the evidence for it being a pyroclastic material. However, macroscopically very invisible, nothing to be measured here, and that's why we had to use a lot of magnetic methods. Methods were, of course, field mapping, structural geology, a little bit of physical volcanology, some optical petrography you've just seen, and then we use the methods of rock magnetism, for example, AMS, which shows us the magnetic fabrics, and I will explain this right away. Anisotropic magnetic susceptibility, or short AMS. What is susceptibility? Susceptibility is the ability of every material to get magnetized. Every material has that. When you put something in a magnetic field, it reacts somehow to the field and it gets magnetized. The magnetic field H, the susceptibility K, and the final magnetization M. For example, when you have diamagnets, which work the worst with magnetic fields, they tend to have the opposite field than there's applied to them. But the opposite, for example, ferromagnets, they get very much magnetized a lot. They respond very nicely, and very often they even have the remanent magnetization afterwards. Something they still are magnetized after the removal of the outer field. However, the anisotropy, the susceptibility can sometimes be different in different directions. That's especially for minerals with crystal lattice, where, well, because of many reasons, like the orbitals of electrons, the inner electromagnetic structure, the susceptibility is different in different directions, and thus we have the anisotropy. Through this, we can measure sometimes, just long story short, through AMS, we can see preferred orientations of the minerals if they are somehow oriented in the rock that we cannot measure macroscopically, like the ones we have here, we have to use this to see what's the fabric there actually like. Just few more terms about what the AMS actually is. It can be nicely portrayed as the anisotropy ellipsoid with three main axes: the maximum, intermediate, and minimum susceptibilities, principal susceptibility, where the maximum, nicely, that's magnetic foliation, magnetic inclination, magnetic foliation on the other side is the K1, as written here. K1 is the maximum, K3 is the minimum. So K1, K2 plane is the forms the magnetic foliation. Other parameters that we often use are, of course, some mean susceptibility, an average one out of these three axes. Second of all, degree of anisotropy. That's basically just a ratio between the maximum and minimum susceptibilities. And shape parameter, a little bit more complex equation, but still simple. This just tells us how the ellipsoid that we use, how is it shaped. It can be, there are like two end members. It can be either prolate, which is prolonged, a cigar-like structure, or it can be oblate, which means it's a disc-like, it's like smashed disc, I don't know, pancake. That's what, how you can imagine it. With this, you often have to use, of course, some additional magnetic methods that we use to see what was the signal of these magnetic fabrics. Not everything that emits the magnetic signal is desirable, and it's important to see how it actually is working in there. So the most important one here is the dependence of the susceptibility on temperature. Easily, we just measure the susceptibility in different temperatures. And the shape of the curve can tell us what the behavior of the material, and that's usually how we tell, like, okay, that's ferromagnetic, that's magnetite, that's paramagnetic, I don't know, biotite, amphibole. And to specify this even better, we use also hysteresis curves and first order reversal curves, which tells us just in higher detail what these actually are. Let's move to the results themselves and the magnetic mineralogy, as we just said. In the Teichweg member, the oldest one, the fabric is mostly formed from paramagnetic minerals. We have just very low susceptibility, does not react well. However, all the others show nice Curie temperatures. You might have heard about this. That's the temperature where you have, I don't know, in this case, it's nicely seen, high susceptibility, and suddenly at about 580 degrees Celsius, it changes to low susceptibility. That's Curie temperature. From ferromagnetic, it's turned paramagnetic. That's special for magnetites. It's good that we see them here, because then we can tell the magnetic fabric is quite reliable, especially when we look at the hysteresis curves. Just to say it very bluntly, Teichweg, the oldest one, and the youngest one, Medvědí vrch, there are finally, in the end, we just tell they are paramagnetic. However, all the others are just formed, the magnetic signal is mostly formed by multi-domain magnetite, which is very good for this study. When we analyze the fabric itself, first we had to do the tilt correction. Easily, we have the rocks in some position nowadays. We take them, we measure them, but we want to know what were their fabrics before, right? So in their original position. For that, we need them tilt corrected, and that we manage thanks to the ash bedding, asphalt bedding, as said previously. After this correction, the oldest member, Teichweg, showed mostly nice oblate to disc-like fabrics, parallel, mostly with flow foliation measured macroscopically. And well, this just showed us the nicest behavior, even in recent ignimbrites, when people measure, I don't know, 5,000, 100,000 years old ignimbrites. This is what it usually looks like. So 300 million years old ignimbrite can still look like that. The younger ones, however, they suddenly got more prolate, more the cigar-like, and their fabrics got steeper at some point, a little bit different, a little bit more difficult to average something, but this just seems to be that they underwent some sort of welding, maybe even starts of rheomorphism when it ductily, some ductile motion happened and reoriented a little bit the fabrics themselves. Most interesting one is the přední cínovec here in the low part, because the magnetic lineation points northeast, southwest. Yes, northeast, southwest, sorry. But the K3 axis, which is the, as I said, the axis to the foliation, forms a girdle. And this girdle, just we can see that the foliation probably rotated a little bit along the lineation. From this, we think that probably the rheomorphism, which a rheomorphism is secondary flowing. When the ignimbrite is a very hot mass of gases and rocks stopped, it was still so hot that it started to flow again. That's secondary flow, and that's called rheomorphism. We think that's what happened here, and this folding is actually this secondary folding is what causing this. Medvědí vrch, the last member, I will leave out of the analysis for after this, because there were just very few localities where we could sample, and the statistical analysis wouldn't be anything important. When we look to, then we had to also do the pyroclastic flow directions. That's what interested us, right? Where was the center of the eruption? Where did it went from? We used the classification of Agro et al., which basically it's mostly put on the K3 axis, the minimum susceptibility axis that actually showed the direction because of imbrication. If you have sedimentary flow, which also happens in the pyroclastic flows, imbrication, sediments deposits these grains in certain order, and the minimum susceptibility can show us the direction this way. The relationship between these and the magnetic lineation then can maybe tell us when the flow was more laminar, then it was almost parallel, or it was more turbulent and it got more perpendicular. In a Teichweg member, the oldest one, the good-looking one, the nice one, the magnetic fabric pretty much coincides with the magnetic fabric and magmatic fabrics were pretty much in unisono. They showed us pretty much the same results, and the flowage itself seems to be from east to west. So placing the source probably on the eastern margin. With the other members, Tuxstein Permenáč and Vlčí kámen, they were probably sourced. They also showed this western or northwestern direction, but also the other way. So the volcanic center, the vent that sourced all these ignimbrites was not very sure if it was on the eastern or western part, but it seems that all these were pretty much the same. Přední cínovec, the last one that's not even here, because of the rheomorphism and heavy welding, we could not really well define what direction it probably had, but this one is also connected with some extra caldera ignimbrites, and thanks to the dating in other studies, we were able to connect it with the dike swarm on the north. That's the most important part. Let's see how the story went, and let's talk about it. First, the small voluminous members like Teichweg were sourced in the eastern margin. They went to the all around in the intracaldera setting. That means they went to the west. They get probably slightly welded. And thanks to that, we have those nice fiamis. The other two, Luxembourg Pravenach and Vlčí Kámen, these were probably sourced on both sides. We cannot tell with certitude which was like eastern or western margin. However, these were probably even more hotter. They were more voluminous and more welding occurred, maybe even sometimes start of the rheomorphism. Not that clear over there, but all these were before the 314 million years. During that time, we had a dramatic switch, we could say, where the biggest, the most voluminous eruption occurred of the Přední Cínovec, which was sourced in the, not very visible here, in the Seiderberg visible dike swarm in the north. And these eruptions are even connected to some extra caldera ignimbrites. These are 30 kilometers to the south, and they are still about 30 meters thick. So the eruption must have been quite big. This we study, and this I study now during my other project, continuing this one. And my supervisor Filip Tomek, in his work from 2022, they also found out that when they correlated, there's a layer of ash in all of the basins in Bohemian Massif. When they correlated this, they found out that the ash from this eruption probably went up to 200 kilometers to the southwest. So the eruption, caldera forming eruption, which was the cause of all this, was probably very big. After everything calmed down, some intrusions in place themselves later on, making a little bit of resurgence. These were nowadays mostly connected with, there were probably a lot of hydrothermal system back then, and they're connected with ore deposits nowadays, and were very interesting to study. As for example, they are now they are searching for lithium there, which is supposed to be like one of the biggest lithium deposits in Europe. In summary, what we found out, AMS, even though for such an ancient caldera system, it can be still used, it can still show us some interesting results. The magnetic fabrics was signaled here mostly from multi-domain magnetite that was in the larger eruptions, and the small ones was probably some ferrous paramagnetic minerals like biotite or amphibole. The pre-caldera ignimbrites before 340 million years, they were flowed towards the west or west-northwest, or at least in the west-east directions, placing the center mostly on the eastern margin or a little bit east-west margin. And they got moderate to higher degree of welding afterwards, after they were deposited. At 340 million years, the biggest eruption took place, sourcing the Přední Cínovec ignimbrites. And this ignimbrite went southward, even like the rheomorphic fabrics, the folding was like perpendicular to this direction. Interesting. Yeah, it experienced a lot of the rheomorphism because it was very big, proximal, hot mass got still deposited and could still flow a little bit. It still got a lot of energy, a lot of potential. Afterwards, the caldera system, the activity, volcanic activity of this system was finished by emplacement of shallow level granites and the hydrothermal system that caused some of the local resurgence. Thank you for your attention, and I hope you liked it. Hello.
So I didn't see very well at the end. You have been showing pictures from the field. I suppose that some of these levels, all the levels, volcanic levels, and everything is outcropping as well. And the question is, can you, for example, determine already how the lavas or the pyroclasts were flowing from the outcrops in addition to what you did on the
They only, I'll get to go a little bit back. Here, this was actually the only outcrop that we could see it. And this outcrop, we could match it with the magnetic fabrics. And from that, we find out, oh yeah, it still matches. It works for this. Directions at this place, they, even the magnetic and the non-magnetic, they work together. However, rest of it, like 90–95%, this was really just the one locality with something measurable. All the rest was like this, macroscopically invisible. So we had to use some sort of other resources.
And the second question is at a bigger scale. So this magnetic activity you show in part of the north from Spain, but when you go to the Pyrenees, to the Cantabrian Mountains, everywhere, we have always the same age dynamics, which are linked to the post-Paris. Do you have an explanation for this huge system of magnetic activity all over the Paris system?
Well, yes. First of all, my dissertation is quite a lot based on like the comparison of late Variscan volcanism between the Bohemian Massif and Pyrenees and the Iberian Massif. But of course, it's not possible to do this in just one dissertation. I think it's more like 10 years of research. The thing is, I think that was during the collapse of the whole orogeny when all the fractures, all the faults got a little bit, they got a little bit more of space, and the buoyancy of the mantle or some sort of the hot material from beneath could go up. So during that time, yes, even in the Bohemian Massif, these parts, all these were sourced during the late Variscan when the orogeny was relaxing, when it was collapsing. Yes. Basically, yes. There are some trends. For example, here it was more like the older ones are in the southwest, and towards the northeast, it's getting younger and younger. So it depends. There are some. This needs to be, I think, one of those things correlated. However, for example, in this these pictures are from the study of it's not visible, but right beneath this dejar de compartir, there's the citation. It's from our Vice Dean Jirka Žák, and they made this nice study when they compare these ages of all the magmatic bodies in place during the Variscan orogeny and in the late stages of the orogeny. So they've seen some patterns here. Not sure how is it about with the Iberian Massif. This, I think, yet have to be more correlated, or maybe there's some study that I did not see. Welcome.
More questions? And I have one in line with the Thomas question, and you said that some of your samples are quite homogeneous and you cannot see it in the outcome of the delineation. But have you seen any gradation of the size of the class in the outcrop exposure, or is it
No.
to see?
No, it's not visible. It's very limited by the outcrops. It's still the whole Bohemian Massif. One of its disadvantages, we have everything there. When you look at all the rocks, we have all different kinds of metamorphic, sedimentary, volcanic rocks. We have it all there somehow. But it's very old, peneplenized, I think is the word. And there's just quite a thick layer of soil everywhere. So you don't always get to see the whole gradation, or you cannot see everything. In this case of when you can see all these purple dots were our stations, and they just look the same. There was even the classification of the members is a little bit different based on the composition. Nowadays also some geochemistry, model distribution, I don't know, minerals, but it's not very visible between the inside one member. It's not visible how much does the composition change. It's very much similar all the time.
And second question, I don't know the geology of the area, but do you think that the younger tectonics can affect these directions in some way?
Yes, that's a good question. That's always a possibility, and we did not really know. However, since the lowermost, the oldest of these members got very much unaffected, and in that case we could see nicely that it still matched the macroscopic and magnetic fabric. They matched, so everything above it, which was younger, must have also not experienced something, some sort of event like that. It was one of the important discoveries I think we made, as because of that we could have said, okay, these fabrics that look like exactly some ductile deformation or something, they must be from different source than tectonic event. So probably rheomorphism or welding. Yeah. You're welcome.